Hello everyone, welcome to our lecture 10 on Mechanics and Materials 1. In this lecture we talk about mechanical properties of materials, and that is corresponding to the third chapter of the Hibbeler book. So before we jump to the mechanical properties of materials, let's remember the big picture of the mechanics and materials. If you remember, we said the key goal of this course is to find a relation between deformations and loadings. But also we said that to find this relation at this upper level is nearly impossible. So what we do is that we go to a different level to find those relations. In order to do that, we defined stresses as representative quantities for loadings, and we learned how to do that in the first chapter of the book. Then we defined strains as representative quantities for deformations, and we learned how to do that in the second chapter of the book, the previous chapter. And now today we want to talk about material and material properties, and that is essentially the connection between stresses and strains. And once we know this, then we have our loop complete. So you can either go this way or you can come this way to connect loadings to deformations. So basically what we want to do is that we are looking for a stress-strain relationship. Before I talk about stress-strain relationship, I need to remind you that we talk about isotropic materials in this course. In Mechanics and Materials 2, you will also learn how to treat anisotropic materials. But for this course, the word isotropic is always an important concept to remember. So isotropic comes from the term isotropy, and that essentially means uniformity in all directions. It's a Greek word, and it combines isos as equal and tropos as way, direction, basically. So basically it says you have equal responses in every direction. So how can we explain it? If you think of a body, for instance, and in that little body you take three pieces in different directions, let's say pieces A, B, C, you cut these pieces and let's say you fix them at the bottom and you apply equal load on top of them. So here, for instance, the force F. Then for each of them, if you calculate a displacement, this would be delta A, this would be delta B, and this would be delta C. So this would be the change of length for directions A, B, and C. Now, if all these directions are having the same deformations, that means if all delta A, B, and C are equal for the same forces, that means these directions are not changing the material response. Or that means the material response is direction independent or it's isotropic. Okay, so remember that we are dealing with isotropic materials. I'm not going to repeat it again and again, but remember for the rest of this course, everything is assumed to be isotropic. Another assumptions that we have also in this course, and we talked about it in the previous lecture, is that we talk about small strains. Okay, so strain, whether you think of shear strain or normal strain, is assumed to be significantly smaller than 1 or 100%. So whether you think of epsilon or gamma, this is much less than 1 or 100%. And then again, remember, the interesting feature of strain is that it does not have a dimension. So actually you can just talk about a number when you want to define it without paying attention to the unit. Okay, that's the first thing you should remember. And the second thing you should also remember is that the material response is usually elastic. And when we say elastic, we also mean linear elasticity. If it is not elastic, then it is inelastic. And for this course, we only deal with a very particular behavior of materials that is not elastic, and that would be plastic, and also not just usual or generic plasticity, but perfect plasticity. Okay, so for most of the materials in this course, we talk about elastic materials. If it is not elastic, it would be perfectly plastic. Okay, so what we want to do now is to define a stress-strain relationship. And then again, if you remember, we had this big picture of mechanics in the previous slide. So this is what we want to do. So for this stress-strain relationship, we are going to begin with a diagram and then explain what different regions in this diagram mean. So imagine you have a bar made of a ductile material, and you apply forces at the two ends of this material. So this is essentially a uniaxial tension test, and because of this, you get a stress that you can calculate. It would be N divided by A, and then you get strain, which you can also calculate. It would be delta L over L. Okay, so we know what is strain and what is stress for this particular test. Also pay attention that we are talking about a particular class of materials that we call them ductile materials. So usually the materials that we deal with in terms of, let's say, mechanics and materials 1, they are either brittle, so you talk about brittle materials, or you talk about ductile materials. Brittle materials are somewhat simpler, so basically for brittle materials, the relation between a strain and a stress would be linear, and then they break essentially, and they show failure due to fracture. So for brittle materials, we are not going to talk about strain stress relationship in details because it's usually just assumed to be a linear and simple behavior. It gets more interesting when you talk about ductile materials, and most of the engineering materials that we use, such as steel, are falling into the categories of ductile materials. Again, in mechanics and materials too, you learn a lot more about these two types of materials, their key characteristics, and their failure modes. All right, so assuming that the material is ductile and you apply forces at the two ends, so it's a uniaxial tension, then you can define stress as force divided by area, and area is the cross-sectional area of the bar. For a strain, you get epsilon equal delta divided by L. So again, delta just corresponds to the change of length, and that is essentially the final length minus initial length. And also I remind you that this is dimensionless. Importantly, the length that you use here in the denominator and the area that you use here also in the denominator, these are initial values. Okay, so maybe you want to put a 0 here to remember. We come to that shortly, but just remember that so far we never asked ourselves if these values are the final values or they are the initial values. Okay, so if we think of a stress-strain relationship, at the beginning of this diagram, we observe a linear behavior. So we see that stress is proportional to strain. So stress is proportional to strain, and that sign means proportional to. And that proportionality factor is E. Okay, so if you assume this is an angle alpha, then E would be something like tangent of that alpha. And also you have seen this particular relation before, and maybe you remember we call this elastic modulus or Young's modulus. But what gets interesting here is that if you have a ductile material, then this behavior does not remain linear like this. Okay, so it gets more interesting, and we want to talk about what happens after this step. So this first region, we call it linear elasticity region, or you would say the material behavior is linearly elastic. And the maximum stress that you can reach for this particular behavior is denoted as sigma prop, indicating that this is the proportional limit. Okay, remember in this region, stress is proportional to strain. So this is the proportional limit. Then after this, if you increase stress a little more, you see a behavior that is no longer linear, but still it's elastic. It's elastic in the sense that if you load the material up to this point, and if you unload it, it will come back to its original points, to its starting points. Okay, so this limit until which the material behavior is elastic, so again you can imagine it goes back and forth on the same line, we call that limit yield limit or yield stress limit. Correspondingly to elastic region, if you want to define it, you can also call it elastic limit. Okay, so remember that sigma y is our upper limit for the stress to behave elastically. So if stress is less than sigma y, the material behavior is elastic. And if we exceed this, then we come up with these more interesting regions that are no longer elastic. Okay, after that, we have this region that we call it yielding. So interestingly enough, in this yielding region, stress is equal to sigma y, and that is ideally, and as we will talk about it shortly, this is what we call perfect plasticity. Okay, so if stress is less than yield limit, this is elastic. If stress is larger, equal this yield stress, then it's inelastic. In this case, we talk about perfect plasticity. Okay, so yielding happens, and then if you increase the deformation or the load a little more, so you keep loading it, if you increase that, then you observe this increasing stress again, and we call that region strain hardening, and this behavior goes on until you reach the so-called ultimate stress. Okay, so after this, something interesting is happening. If you increase the displacement, so if you keep pulling this, then you observe a decrease in stress. So it's no longer increasing, it just actually starts to decrease. And we call this region necking or necking region. This behavior continues until you reach the so-called fracture stress, and that's where your material breaks, essentially. Now, obviously, we would ask ourselves how this makes any sense, because if you remember, we are talking about a extension test. So you keep applying forces, and it's strange that we imagine that strain is decreasing, the stress is decreasing by increasing strain. So what is happening is basically related to the definition of the stress as we spoke before. If you remember, stress is the normal force divided by the area zero, or reference area, or area at the beginning of the test. We call this stress maybe the engineering stress, or nominal stress if you want. So you can define that stress, of course, but what happens, and that's why this region is called necking, is that when you have this member and you keep extending it, at some point it starts to neck in the, let's say, in the middle maybe. And I'm sure you can kind of imagine what happens here. So basically this is what happens, and the cross-sectional area of the material decreases. And that's the reason you see a decrease in stress. But then again, you should remember that you see a decrease in stress if you divided it by its original area. If you did not divide it by the original area, so if you divide it by the actual area, obviously the stress is actually increasing until it reaches the fracture stress. So if you divide the normal force by the current area instead of the reference area, then you get this other stress measure, which we call it true stress. And then obviously that true stress keeps increasing throughout this loading. And that kind of makes sense. So if you think of a true stress versus a strain, this would be your true stress versus strain curve, and that kind of makes more sense. But as long as you know that you define the stress in terms of the engineering stress or in terms of the reference area, then of course you may want to also look into the other one. Okay, so either way, you should remember that we have these sort of 5 regions to define the behavior of a ductile material. But also I need to emphasize that this graph that we have here is not to scale. Okay, so the region, for instance, the second region here, the region that the material is still elastic but is not linear, this is usually very, very tiny, and we don't really see it. Also, there the sort of range here is, sorry, the range from here to here, this is much, much larger than this one. So you may, for instance, you may think of something like this. Okay, so this linear region or this elastic region is much, much smaller than what happens afterwards. But I drew it like this to identify these 5 regions specifically. And as I said, ductile materials are more interesting in terms of elastic behavior or in terms of stress strain diagram, but brittle material also follow the first region similarly. So this sort of behavior, as long as we are in the elastic region, it's the same for brittle or ductile materials. All right, so that means if we think of ductile materials such as steel or brittle materials such as cast iron, we can always think of the material behavior as being linearly elastic, or let's say we can assume that linear elasticity defines our material behavior. And then again, remember, we also always talk about isotropic material behavior. And as I mentioned previously, the word linear simply indicates that stress is proportional to strain, which can be written like that. And then this concept is identical for normal stress and normal strain, as well as shear stress and shear strain. And then you define these proportionality limits, the proportionality coefficients E and G, and we call E the elastic modulus or Young's modulus. We call G the so-called shear modulus. Okay, so let's just finish this by now extending that linear elasticity to inelastic material behavior. And then again, we are only talking about perfect plasticity, and this is valid if we talk about ductile materials. So if your material is ductile, and if you want to think what happens if we reach the yield stress, we idealize the material behavior by this graph. So basically, we assume that we have this linear region for which, again, the elastic modulus is essentially the tangent of that angle that you get. Or if you assume this length is 1, this would be E. And then after you reach this, let's say, maximum strain for elastic range, you come to the so-called inelastic range. And for inelasticity, we assume that the material is perfectly plastic. It means it only goes straight. And E is larger than 0. Now you can think of the same for shear strain relation, assuming that you have this linear region where your shear modulus is tangent of the angle alpha, and then after reaching the maximum shear strain where the material is still elastic, after reaching that you come to this perfect plasticity region. And also shear modulus, as you can imagine from the picture, it should be positive. All right, so we have elastic range, and then we have the inelastic range. In this case, perfectly plastic range. In the elastic range, if you unload the material, you always come back on the same line. So basically you go, let's say you load the material until this point, and when you unload it, it comes back to its original position. The same goes if you load it by shear loading. If you unload it, it comes back to its original position, which is 0. However, if you reach the so-called plastic range, if you load the material and then you come and reach this point, for instance, when you unload it, when you release the force, it comes back parallel to the elastic line, but it does not go to 0. So you end up with this much strain in the material, even though there is no load on it. So remember, this line means that stress is 0. So if there is no stress on the material, but if you have reached the plasticity region, that means there would be a permanent strain remaining in the material or a plastic strain remaining in the material, and we show that by epsilon p. Okay, so permanent means that the strain remains in the material although there is no stress. The same is exactly happening to the behavior of the material under shear stress. So if you increase the deformation and you come here and you reach the plastic region, when you unload it or when you release your stress, then you come to the point where you have permanent strain or plastic strain or permanent shear strain. The next topic we want to talk about is the so-called Poisson's ratio. Now, if you think of a bar that we had maybe in our experiment, and now I'm just talking about elastic region. So forget the complexity of ductile materials and plasticity. I'm just talking about a simple elastic behavior. If you have a bar and you elongate the bar in the direction L, so you get L plus delta L, such that delta L is positive, you can imagine that in the other direction, although you do not apply any force, you get a contraction. And then again, important is that these are the loads that we apply. So we apply the loads only in the horizontal direction. So we apply no load on top and the bottom. So it's not that we are compressing it. We only extend it in the, let's say, in the x direction, but then automatically it contracts in the y direction. This effect is called the Poisson's effect. So basically the idea is that if you have a longitudinal strain defined by delta L divided by L, and then again you can imagine this is positive if you have extension and it's negative if you have compression, but let's say this is your longitudinal strain, then even though you do not define or you do not apply a force in the lateral direction, still you get a strain also in the lateral direction, and that would be delta D over D. And then again, in this particular example, we can see that its extension, so delta L is larger than 0, but also you can imagine when this thing happens, usually when you extend the material in one direction, it contracts in the other direction. That means delta D is less than 0. For very particular family of materials, you may have delta D equal or larger than 0, but these are usually exceptional materials. Okay, so we talk about that also, but this is not very common. Okay, so based on what we have now, we can define Poisson's ratio. Now, Poisson's ratio is the ratio between lateral strain and longitudinal strain. So you divide lateral strain by longitudinal strain, and then you introduce this minus sign because, as we said, usually for most cases that we know, when delta L is positive, delta D is negative. So you want a coefficient to be positive, and for that reason only, you just apply or you just introduce a minus sign. So the upper limit for Poisson's ratio is 0.5. And then maybe you can imagine that this comes from the fact that if you have a material and if you extend it in one direction, in the other direction it may contract, but it cannot contract too much. So it always contracts a little, and for that reason we get 0.5. I'm not going to prove this geometrically, but you can. Also, if you think of a simple test, let's say you think of a square here that before the formation it's just square, and then after the formation we elongate it in the x direction. If it contracts in the y direction, Poisson ratio is larger than 0 based on the definition we have. Now, if nothing happens to it, so let's say you have a longitudinal strain but the lateral strain remains 0, if that happens, then Poisson ratio would be 0. Okay, so Poisson ratio 0 corresponds to the case where you don't get any lateral contraction due to longitudinal extension. So from this picture, maybe you can now imagine that Poisson's ratio is a measure of material incompressibility. So it tells you how much compressible or how much incompressible a material is. And then again, the upper limit means the material is fully incompressible. Okay. So if you cannot change the volume of the material, you can only get to the fully incompressible material ratio, or the fully compressible Poisson's ratio, that's 0.5. Okay, so for usual solids, and in this course definitely, Poisson ratio is between a quarter and 1/3. For some materials like cork, Poisson's ratio is 0. And then if you think actually where cork is used, we use cork to seal the bottles. So now you can imagine if cork has a large Poisson ratio, it would be very difficult to seal a button. It's to seal a bottle with it, because when you push it inside the bottle, if it has a larger Poisson's ratio, then it would like to expand in the other direction, and that makes it difficult to use. So this particular property that it is essentially fully compressible, it makes it a suitable material for sealing. Then you have this very particular family of materials that are called auxitic materials, and they have Poisson's ratio that are less than 0. And these are usually very difficult to imagine, but essentially that means if you have a square and then you expand it or you extend it in one direction, also in the other direction it's going to extend, or that means you get like an expansion basically. Okay, so this would be your final material. So these auxitic materials are not usually observed in nature, but you can manufacture them, such as let's say metamaterials. Then the upper limit for Poisson's ratio is the so-called incompressibility limit, and that's 0.5. The lower limit for Poisson's ratio, however, is not the fully compressible. So this would be fully compressible limit. But then you can even go lower than that, and then you can come all the way down to Poisson's ratio -1, and that is the lower limit, and that's basically a thermodynamic limit. So Poisson's ratio is between -1 and 0.5, and I'm not going to prove it here, but you can certainly learn more about it. Talk to me if you would like to. All right, so if you remember now, we defined E, elastic modulus, we defined shear modulus, and now we define Poisson's ratio. So the question should be asked, how many of these material parameters then can we define? The answer is that you need only two. In other words, Poisson's ratio is not an independent material parameter. So if you know what is E and what is G, you can calculate the Poisson's ratio. Or otherwise, if you know what is E and what is Poisson's ratio, you can calculate the shear modulus. Okay, so you always need two material parameters, and then again, we are talking about isotropic linear elasticity. So for isotropic linear elasticity, you only need two material parameters. So we are going to learn a little bit more about material parameters and mechanical properties of materials through a few examples together. Exercise 1 is similar to problem 3.6 on page 108 of the book. An aluminum specimen shown in the figure has diameter of 25 millimeter and length of 250 millimeter. I am showing the lengths by subscript 0, indicating that is the initial length. The force F of 165 kilonewton elongates the specimen by 1.2 millimeter. Determine the modulus of elasticity, also determined by how much the force causes the diameter of the specimen to contract. Take shear modulus for aluminum 26 gigapascal and yield stress for the normal stress 440 megapascal. Note that we do not have modulus of elasticity, but we can calculate it from the first part of the example. So the first thing we want to do is to calculate normal stress and normal strain for this example. Normal stress is the normal force divided by area, and then again, area is the initial area. Normal force is 165 kilonewton, that's 165,000 Newton, and area is pi over 4 times d squared, and d is 25 millimeter, which is 0.025 in terms of meter. That gives us stress of 336 megapascal. Then we calculate strain. Strain is the change of length divided by length, and then again, this length in the denominator would be the initial length. The change of length is 1.2 millimeter, the initial length is 250, and then strain would be 0.0048, which is dimensionless, but if you want, you can write it as millimeter over millimeter or as meter over meter. It doesn't matter. So we need to quickly check if the material behaves elastically or inelastically. For that, we compare the normal stress by its yield limit. The yield limit is 440 megapascal. What we have here is 336.1 megapascal. So because of that, you know that the material behaves elastically. That means stress is related to strain via the so-called Hooke's law. And from that, you can calculate the modulus of elasticity, or the Young's modulus, by dividing stress by strain, and that gives you 70 gigapascal. So the modulus of elasticity for aluminum is 70 gigapascal. Now the next thing we want to do is to calculate how much it contracts. So in order to calculate how much it contracts, we need the Poisson's ratio. If you remember, Poisson's ratio is not an independent material parameter, so it can be calculated from E and G. So now we have E and G is given. If you insert the values, so 26 gigapascal was G and E is 70 gigapascal. If you insert the values, Poisson ratio would be nearly 0.35. So about 1/3. So the last thing you want to do is to insert the strain that we calculated here, and using the Poisson ratio, you want to calculate the lateral strain, and then from the lateral strain, you can calculate the contraction in the diameter. So if you do that, you get lateral strain to be minus 0.0017. And you remember the definition of the lateral strain is delta D by D. And that gives you delta D of 0.042 millimeter. There is a minus sign here, so you can either write it with minus sign or just remember that it would be a contraction. So if you remember, the example shows us a bar that you extend it in this direction. So essentially that means if you extend it in that direction, in the lateral direction, it's going to contract, and the diameter contraction is 0.042 millimeter. Exercise 2 of today's lecture is similar to problem F316 on page 112 of the book. A 20 millimeter wide block is bonded to rigid plates at its top and bottom. When the force P is applied, the block deforms as shown in the figure. So essentially you have the square block here, you apply force P, and due to shear stress, it's going to transform to a parallelogram. Determine the permanent shear strain in the block after P is released, and also determine the force P. The stress-strain diagram is given here, and as you can see from the example, it's a shear loading. That means you need to work with shear stress and shear strain as opposed to normal stress and normal strain that we did in the previous example. So the behavior is elastic, perfectly plastic here. And that means, for instance, if you reach a point here and you release it, you come back to a point, and what is remaining here, that's your permanent strain. All right, so you can calculate the shear strain gamma by looking at this angle, and the angle here, which corresponds to the shear strain, is the arc tangent of 3 millimeter divided by 150 millimeter. And that gives you 0.02 radian. Now that means we are somewhere here in this graph. So if that is 0.02, this is where we are. So let's say point A. Now that means you load this, you come to this point. Now, when you release the load P, the force P, it's going to come back parallel to the elastic line. If it comes back in parallel, that means this part, it would be 0.005, which tells you what you have here would be 0.015 radian. Okay, so the permanent shear strain would be shear strain minus what would be recovered due to the elastic regime. And then you get this much left in the material, and that's the permanent part of the shear strain. So that's what we wanted to calculate for the first part. For the second part, you are asked to calculate the force P, and force P is shear stress times area. For the area, you can see that the length is 150 millimeter in this direction. The width is given to be 20 millimeters. And shear stress is 130 megapascal, because if you remember, we said we would be somewhere here, and that means we are at the yield stress. So the yield stress is 130 megapascal, and we are exactly multiplying the shear stress, which is equal to the yield stress, times area. You get the force 390 kilonewton. The third and the last exercise today is similar to problem 3.4 on page 105 of the book. A bar made of steel has the dimensions shown in the figure. So it's 1500 millimeter in length, 100 millimeter wide, and 50 millimeter is the height. If an axial force of 80 kilonewton is applied to the bar, determine the change in its length and the change in the dimensions of its cross section. Also, you are told that the bar behaves elastically, indicating that whatever stress you calculate is smaller than the yield stress. So you don't have to worry about that part. All right, so if we define this coordinate system for simplicity, let's say the main axis is the x-axis, then the normal stress would be the normal force divided by area with the normal axis to be the x-axis. So the cross-sectional area here would be 100 times 50 millimeter squared. So 100 millimeter is 0.1 meter, 50 millimeter is 0.05 meter. So that's the area of the cross-section with the normal axis to be the x-axis. And then the normal force is 80 kilonewton, so 80,000 newton. That gives you the stress in the x direction to be 16 megapascal. Now for that stress, you can calculate strain, and then again, because we know stress is less than the yield limit, or we know it's elastic, you know that stress-strain relationship would be the so-called Hooke's law, and from that, you calculate the strain in the x direction, and that would be 80 micrometers. Sorry, that would be 80 micron. So it's a dimensionless parameter, so it doesn't have any particular unit. So it's dimensionless. So it's 80 micron. Now, if you want to calculate the change of length in the x direction, that would be epsilon x times L. And then again, this is exactly the inverse of this relation. So the definition of the strain in the x direction. So all you have to do, you insert the strain, and you know the length, the initial length is 1500 millimeter, and then you get the change of length that is 120 micrometer. Now to calculate the strain in the Y and Z direction, you can use the Poisson ratio definition. So Poisson ratio is minus epsilon or strain lateral divided by strain longitudinal. And if you do that, you can see that the strain in the Y and Z direction is minus 25.6 micron, or minus 25.6 times 10 to the minus 6. And then again, it's dimensionless. So what you want to do next is to calculate the change of length in the directions, in each direction. So now you know in each direction the strain is this. But in order to calculate the change of length, again, you use exactly the same relation that we had here, but for each direction separately. So delta L in the y direction is epsilon y times length in the y direction, which is 100 millimeter. So that gives you minus 2.56 micrometer. And then again, minus means that it is a contraction, as you can imagine. So if you extend it in the x direction, and because Poisson's ratio is positive, then you get a contraction in the y direction. In the z direction, you use the same formula, but now the height is 50 millimeter, whereas the width was 100 millimeter. That means you get half the contraction compared to the y direction. So you get minus 1.28 micrometer. All right, so now we have all the unknowns. This is the change in the y direction, change in the z direction, and change in the x direction. And then again, minus here, it just indicates that it's a contraction. Here, it's essentially plus, meaning that the bar elongates and the length increases. All right, so this was our lecture on mechanical properties, and essentially we covered the third chapter of the Hibbeler book. I'll catch you in the next one.